Yeah. All right. So hopefully everybody, looks like there's no one in the way yet. Here we go. We have 2 more people. We'll get you guys admitted. All right. So after last class, a couple things. So I rewatched the video. I realized there's a lot of clicking, and I think it was my mouse. So I'm keeping my mouse way away from the audio, what's being recorded, the audio this time. So hopefully the recordings that get put up on YouTube are a little bit better. I'll also try to kind of keep my volume pretty loud, which might sound for those of you who are in person like I'm shouting all the time. But I know that it doesn't record it real clear. If you guys are having any problems on Zoom hearing me, let me know. I naturally walk around a lot, and I'm realizing I have to kind of stay put here. Otherwise, as I get further away, you can probably notice you don't hear me quite as well, right? So I'll try to be better at that. The clicking is still there. I'm not even doing anything. Okay. I don't think what else could be. I played around with it last night. Yeah, I don't know why it's doing that. Oh, okay. So I'm not going to use the camera a whole lot, so I'm going to try to do this. Let's try just using. Let's just try using this. You won't be able to see me quite as well on Zoom, but I don't think I'm going to have the camera on a whole lot today. We'll be using this Elmo thing in class so you can see me do like essentially board work. Hopefully in the chat, if anyone wants to let me know if switching that camera kind of helps. Hopefully that clicking noise can get rid of it. I played around with a whole bunch last night and I still couldn't figure it out. I thought it was the mouse because when I was using the mouse pad. Okay, it helped the clicking, but still didn't go away. So hopefully I can figure out if someone can catch why that's happening. But until then, I apologize. Hopefully Friday I'll have that figured out. I wasn't even aware. So if something like that happens, people on Zoom, don't be afraid to speak up or say something because I wasn't aware it was going on. And now that I am aware, I can try to fix the problem, but someone made me aware of it last night, and so that's why it still hasn't been fixed. So let's go. Got our seating chart here for today. We don't need this anymore, hopefully. We'll kind of dive in where we left off. Which ones? I have to shut that down. This is where we stopped last class, right? So. We went through these at the end of last class. I'll shut the door here real quick. Okay. So obviously this is business statistics, so we'll be looking at a bunch of different data sets throughout the semester. I pulled this one, kind of a short, small little data set. Nothing too crazy. I'm aware that not everyone likes sports, so I'll try not to use a lot of sports data, but I will occasionally use some just because there's so much of it and it's easy to get. But it really doesn't matter, right? I've got a bunch of names here. I've got their position that they play on the baseball field, and I have their salary. But this, if we look at the 3 variables here, so we've got the player's name, their position, and their salary. I mean, that very well, those 3 variables could be any company, right? This could be John Smith, who's a office administrator who makes $25,000 a year, right? We just have a little bit different kind of numbers here. So every single row we have in a data set, we'll call that an observation. Sometimes you'll see it referred to as an element, but that's they're kind of just interchangeable. Every single column we have, that's why I said we have 3 variables here. Every column records some variable for every single observation, right? So for this first observation, we've got the player's name, that's the first variable, their position recorded, second variable, salary, that's the third. Right? So columns are variables, rows are going to be our observations. Okay? Now, a lot of examples I'll use, typically our observations are going to be people, but they could be companies, they could be at the country level, they could be, a bunch of different things, but usually we'll see them individuals, but they could be aggregated up to the county level, state level, whatever we would want. So we'll see a couple different types of data. So qualitative and quantitative. You probably have maybe heard of this before in another class. Qualitative simply just means we're recording something that isn't a number. That might be the easiest way to say it. So layman's, it's not the technical definition, but essentially anything that is recording a characteristic for that observation that isn't numerical, right? So this might be like if we had a huge used car data set, we could be collecting the color of the car, right? That's a qualitative variable. Okay? A quantitative variable would be some type of numerical variable, right? We're recording a number down to identify this characteristic of the observation. This could be the mileage of the car, maybe the year the car was made, right? Some type of numerical observation. Sorry, numerical value that we're recording for the observation. Right? Let me double check here. There we go. I want to make sure that if people join in late, getting everyone. One more question in chat. Okay. So this really just kind of breaks it up into two categories. Once we have these two categories, we can kind of break it down even further. So we have qualitative variables. We can break those down into nominal, is a type of qualitative variable. Nominal variables is something where there's no intrinsic value to whatever we're recording. This could be like if I'm recording a data set with all of you as my observations, and I record your hair color. That tells me nothing intrinsic about you, right? So if we had hair color, you can think of maybe we're recording gender, we're recording baseball positions like we had in that previous data set, right? So this position variable, this would be a good example of a nominal variable, right? Even the name variable here is also nominal, right? It's non-numerical, so it's qualitative, and it's nominal because it's not telling us anything intrinsic about those observations. Okay? Ordinal variables are also qualitative, right? But ordinal gives us some way, usually in which we can kind of rank the data or rank the observations, or categorize them where there is some intrinsic value to it. So for example, at the end of the semester, you always have these student evaluations and they ask you, overall, this instructor was blank, fill in the blank, or they ask you a bunch of different questions. And you can respond with strongly disagree all the way up to strongly agree. So these are non-numerical, right? These are just words that I'm recording. If you put agree for your observation, your response would be agree. It's not a number, so it's qualitative, but it's not nominal because I know that if you tell me you strongly agree that this person's a good teacher, well, that means you think they're better than the person who said strongly disagree, right? I can kind of rank the observations based off the response to this variable. So there's a lot more value, I would say, you might say, with an ordinal variable than you would have with a nominal variable. Okay? So some other examples we can think of. A lot of times we'll have an individual's education level. Well, I can say someone that just has a high school degree has less education than someone who has a college degree, right? There's not a number assigned to this. I mean, technically, the number of years to get a high school degree could vary. The number of years to get a college degree could vary. Especially if we look at the category of some college, well, I could have 1 year, 2 years, 3 years, but if all I have recorded are these words, well, it's not a number, it's just qualitative, but I can kind of order or rank the variables. There's some intrinsic value to that, and so we would call it an ordinal variable. Okay? So another good example would be if I wasn't able to observe someone's actual percentage grade in class, like I think when I submit these things to the registrar, I'm just submitting letter grades. So if I just have letter grades, it's not a number, right? It's just a letter with a plus or minus next to it, but I can rank students based off of that, and so we'd say that's a good example of an ordinal variable as well. Okay? Any questions on that before we keep moving? This is pretty straightforward. This kind of definitional stuff. We go to quantitative variables, and this is probably what we'll focus a lot more on throughout this course. The first type of quantitative variable that we'll kind of break it down into is discrete. Right? So if a variable is quantitative, it's a number, it can be a discrete quantitative variable. We would say that a discrete variable is finite, or there are gaps in between the observations we could see. So if I'm thinking about a discrete variable, this would be like if I asked you, how many kids are in your household? You could answer 0, you could answer 1, 2, 3, but not 1.5. Well, I hope you're not going to answer 1.5, right? You shouldn't have half a kid running around. So, right, if it's discrete, we're going to see these jumps. Another way to usually think about this is it's an integer, right? Typically, these discrete variables are integers. We could get real specific about this, and I'm sure there's a variable out there that we could see that's being recorded that it jumps by halves instead of 1. So it doesn't have to be an integer. It's just more often than not, a discrete variable will be an integer. It could be that, you know, what's the response to a certain variable? You could only see 0, 0.5, 1, 1.5, 2, and that would technically be discrete. But for the sake of what we're doing in this class, anytime we deal with discrete variables, they'll be integers, right? So 0, 1, 2, 3, 4, 5, 6. But you can't see anything. If we have a little graphic here, maybe. Oh, there we go. I can't see anything in between, right? I could see 1, I could see 5, but I can't see 7.3. Right? That would make it non-discrete. So that's pretty straightforward. Continuous variables, basically the opposite of discrete variables, right? Instead of jumps, there are no jumps, and so technically we can see any number. I could see 34.31295. But I can see any number if it's a continuous variable. All right? So examples, you know, we can measure height. If we had a good enough measurement, you know, tool, we could measure that down to whatever decimal we want. Weight, salary is a good one. We could see 2, we could see 5, but we could also see 6.329. Right? So that's kind of our difference between continuous and discrete. Is continuous is we can see any value. Right? And this will be really important for us once we start talking about distributions to know that we're dealing with continuous and not discrete variables. What do I want to say here? Anything else? Oh, this is where, just to make a point, because I occasionally will have someone who's maybe taken a stats course or something before and they want to really nail me on this. So, right, income, right? Why could I argue that that's technically not a continuous variable? Think hard about this. So discrete, right, means that you just see jumps. I said usually the discrete variable is an integer, but it doesn't have to be. So why could you argue that salary here isn't technically continuous? Well, I wouldn't say with taxes. I see what you're saying because you're going to jump the numbers. It's something a little bit different. So don't think so much about where the salary is coming from, but can I get paid in anything between 1 and 2 cents? Maybe digitally now this has changed a little bit, but if we go think about physical money, right? I can give you 1 penny and I can give you 2 pennies. I can't give you 1.5, right? So you could argue salary may not be technically continuous because it really is stopping at that second decimal. But like I said, for the sake of this class, I mean, we're not going to get into real deep theoretical arguments. If it goes out to a decimal, like 2 decimals, that's close enough for us to be continuous, right? There's, you know, some theory in there we could dive into that, you know, if this was a pure stats course, maybe we would, but since we applied stats, we're not going to worry about that. Also, technically, if you're right, like through the IRS and through your job, you actually will see on a pay stub sometimes you actually can get paid out past that second decimal. So technically, even there, I would argue it is continuous, but some people get tripped up by that a little bit because there could be small gaps if we were limited to our physical money of a penny. Right? That's kind of an aside. So we'll go back to that data set I showed you earlier, and here I rounded it. The actual data set does have these out to the second, third decimal, but salary here we would have as a nice continuous variable that when we're looking at that data set from earlier. Okay, different types of data we'll see, and I'm going to go through this quick because I'm not going to like ever quiz you or anything on this, but just give you an idea when we start looking at data sets, or you might hear these terms being thrown around. Cross-sectional means that we're recording information about several subjects or observations at one point in time, and not just one point in time, but the same point in time. So that'd be like right now, if I recorded every single person in this room, I guess maybe on Zoom, I recorded your age right now. Right? That would be cross-sectional because I'm recording several different individuals, elements, observations, but I'm recording it all at just one point in time. It's not like I have your height when you were 7, 13, 18, I only have it at one point in time, which is today. Right? So that'd be cross-sectional. That's a lot of the data sets that we'll look at. Time series, which we'll dive into, I think we might get to that today, is when we have like one subject, but we've got it recorded at multiple points in time. So the easiest one usually for this, well, I'll go with the height example still. Let's say I chose one of you, and I somehow, I don't know, got your recorded height at every single year of your life, right? Well, now I have one subject, one person, but I have multiple recorded observations in different years. Right? So that'd be time series. Another example for this would be if I took the US unemployment rate and I had it for the last 20 years, right? One subject, the United States, but the variable I'm collecting has multiple observations, which would just be a new observation for each year. Okay? And we'll look at some of these data sets in here in just a second to give you a better kind of visual idea of what that would look like. And then panel data is kind of like I'm taking time series, I'm taking cross-sectional, and I'm mashing them together, right? Panel data is when I have multiple subjects and I've recorded some variable on them at multiple points in time. So that would be like if I had every single person in this class and I had all of your recorded heights at every single year of your life. That'd be a nice panel data set. Right? It's kind of like I've shoved the two cross-sectional and time series together. Okay? And these give us a lot more power. These are usually a lot more interesting. So I can follow people or countries or whatever over time, and I've got multiple different people or multiple different countries I can follow. So here's a nice example of a cross-sectional data set. We've got different countries. We've got 3 variables, but we've only recorded them in 1 year. So multiple different subjects, right? Multiple different countries. And I've recorded each one of these variables just at one point in time. So that's cross-sectional. Right? So the cross-sectional data, even though it's one point in time, we can still have multiple variables. Right? It's just that each one of those variables has been recorded in just 1 year. Right? Time series data, here's that US unemployment rate I talked about. We've got only the United States, so one subject, but we've recorded this variable of the unemployment rate at several different years. Okay? And then the final one, I had some old I-step score data. I think you guys are starting to get too young, but I had all this I-step data in 2009, 2010, 2011. If you were in grades 5 through 8, I believe is what I have. I have like all the I-step scores from Indiana. So were you guys in, come on, maybe you're going back what, 10 years, something like 20. Yeah, some of you might actually be in this data set then, right? If you were in 5th through 8th grade in the years 2009, 10, or 11, your I-step score would be in here, right? But I've got multiple individuals. Now, I don't have names. I've just got student ID numbers. But for the same student, I have in multiple time periods their recorded I-step scores, right? So this is a nice panel data set. We've got several individuals, right? Here I only showed you 3. There's many more. But I've got these variables of the I-step score recorded at different points in time, okay? So that's kind of 3 nice visuals of data sets we'll be looking at, 3 different types. I'll stop here if there's any questions. It should show there. It should give me an alert. So sense it. Yes, if someone said, answer my question. I should be able to. Let me try something else. I'll have to play around with that. It should give me a prompt when someone types in the chat down at the bottom. But I'll keep it better on it. Okay. I think I mentioned this a little bit last class in an example I talked about. When I gave the example of why did they like censor it to the last 10 years when we were talking about that one example of like small market teams, I mentioned something about we're only taking a sample, why didn't we use the entire population? Okay, so to elaborate on that a little bit more, a population data set is if we had every single subject or person or country, whatever we're looking at, we had every single observation that existed. So if I looked at that I-step data, I would say I had the population data set for I-step scores in Indiana, right? Because I had every single Indiana student, right? I didn't leave a single one out. Anyone who ever took it was in that data set. Now, if I only had, say, 5 of the schools in Indiana and the recorded I-step scores for every student in those 5 schools, well, I no longer have the population data set for Indiana. I only have a sample of it. I only have 5 schools. So population is every single, whatever group we're trying to make a conclusion about, whether or not that's one state, the entire world. I need every single person, country, whatever that will be in that population or in that group that I want to make a statement or draw a conclusion about. So one way in which we can try to get at this, right? Let's say I want to know what the average income in the US was. Well, one way I could try to get at that is taking a census, right? Or getting everyone to respond to me somehow what their income is. Now, it's really expensive. We only do it once every 10 years because it's really, really hard to do. And even then, we don't get a perfect response rate, right? Probably the only real way to do, population data also is, something like the IRS, where if you don't respond to them, you are fined or you go to jail or something, right? Otherwise, it's really hard to get population data on things. So usually, we have to kind of settle with taking a small sample, right? So the sample will be a subset of the population, right? If I'm interested in the average income in the US, I don't want to take a sample from Canada, right? It needs to be a subset of the US population. So maybe I randomly select 100 people across the US, okay? So once we have this sample, what we're going to try to do is then make an inference using the sample data we have. Well, they came from the population. We don't have every single person in the population, but based off that sample, we'll make inferences about the population as a whole, right? If I sample 1,000 people and I find their average height, that probably tells me something about the average height in the US. It's not going to be perfect, but it's going to be pretty close, right? So if I take a sample, I can then use the statistics from that sample to make inferences about what the true population value would be. Right? So we call that kind of statistical inference. I kind of already mentioned the reason why we have to do samples. It's just really expensive, to get data on an entire population. It's also just not feasible. Think about it. If I wanted to record or figure out kind of the obesity rates in the U.S., and I go try to get population data and record every single person's weight and height and everything to make to see whether or not they fit this category. By the time I'm done, a lot of those people will have either gained or lost weight, and so they may now be in a different category, right? So it's just not feasible a lot of times to collect population data and still have it be valid even by the time you do get it collected, right? So that's why we use samples, a smaller subset, and we'll talk about some of the issues that just kind of arise because of that. But it's just mainly because of practicality. We just can't get population data a lot of times. If we can, then that's great. We should use the population data, but we just often can't get that. I already mentioned this. Don't worry too much. I'm not going to throw definition questions or anything in homeworks or anything like that. But statistical inference is just that process of using a sample to make generalizations about the population, and then descriptive statistics are basically going to be statistics that we get to try to describe something about either a sample or a population, depending on what type of data set we have. I should repeat that slide. No, it's stuff we've already said. I'm not going to waste my time on that. Okay. So here we start to get to maybe some actual kind of statistics. The first thing we're going to do is try to come up with a frequency distribution. Right? So frequency, right? Frequency is the number of times something happens, or how, So if I look at this little data set, I've got 9, 10 people, it looks like, and I've got their recorded grade for a course. Okay? So what a frequency distribution is going to do is it's going to look at, okay, what are all the possible responses I could see for this variable of grade? And I want to be able to show which one's happening the most, right? So from this group of students, how many A's are there in the class? How many B's are there in the class? C's, so on and so forth. So what I would do is, I would just basically count these up. So look at this, how many A's are there? 1, 2, write down the count or the frequency I saw in that data set for the response of A. How many B's? 1, 2, 3, so I recorded 3. I go through and do that for every single possible response. Now, obviously, for a variable like grade, it's not too tough. There's only 5 possible responses I have here. I guess I could have put in incompletes and stuff like that, but a small number of responses. This gets a lot harder if I have a variable that can take on 100 different responses, right? And so eventually, probably not today, or Friday, we'll start looking at Excel and say, well, even if we didn't just have 5 responses, there's an easy way in which we could come up with these frequencies, right? But you can kind of imagine the most simplistic way is just counting, going through and counting. Now, obviously, if I had, say, every student at Ball State and I wanted to come up with a frequency distribution for that, I don't want to do that by hand, right? I mean, I don't want to do that. I mean, maybe some of you are statistics or something, but I want to use Excel because it can do it for me very quickly, right? And we'll, like I said, we'll get to that on Friday and see how Excel can do this, but at least we understand what this frequency distribution is. We've got the counts or the frequencies for each of these possible responses. And that kind of tells me real quick, well, what's the most common grade? Once I have this frequency distribution, what's the most common grade in this class? One with the highest number, right? So a B, right? I look here, I can easily see, oh, 3 is the highest. That's the most common grade in this whatever class this was. The least common grade would be kind of D and F, et cetera, right? It gives me kind of this nice, quick snapshot of what's going on in that data set. Right? So I can then take it one step further. I've got the frequency distribution. Maybe I want a relative frequency distribution. So with that one, it was kind of easy to see because the numbers were small and I can compare them pretty easily. But maybe I want to show this as kind of the fraction of people who get an A in the class, right? Or I want to make this frequency relative, right? So yeah, 3 people got A's, but how many people were there in the class, right? So what I can do to get a relative frequency distribution is basically just take every single category's frequency, so the number of A's, number of B's, so on and so forth, and divide all of those by just the total number of observations there. If I do that, I will now have the fraction of students who got A's, the fraction of students who got B's, so on and so forth. That's pretty easy to do, right? So if I go back to that Hubs data, I then kind of did the same thing. I used that position variable, and I found the frequency for every different position. Now notice here, there's a weird frequency distribution because every frequency is pretty similar except for the one position of pitcher. So we would have kind of it tells us something unique about the data set right away, that one of these positions is way more common than all the others, right? And that comes straight out of the frequency distribution. But how much more likely, how much more likely is if we chose a player at random, they would have a position of pitcher? Well, we just go through, divide every single frequency by the total number of observations. So how did I get that total number of observations? Well, once I have the frequencies, I just add them all up, right? Because if I have every possible response, so we go back here, if I've recorded every single observation somewhere, right? I counted them in whatever category they belonged in. If I add all these up, it should give me the total number of observations because I've counted every single observation once. So let's say I do that here. 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly, right? It was the number of observations I had. The frequency should add up to the total number of observations. Same kind of thing with this data set. It's just now, here's our frequencies. They add up to 25. We actually can't see the original data here. I'm not showing it to you. I'm just showing you the frequency distribution. So you don't even have to look at the data set here. You don't have to go through and count by hand. You can actually just add up the frequencies and get how many observations were in that original data set to begin with. Okay? Chat questions. All right. So I could go through and do this for every single position or every single possible response to that variable, right? I would then have all these relative frequencies. Right? So how do we go from frequencies to relative frequencies? All we have to do is, I just told you. Anyone? How do I turn frequencies into relative frequencies? So I add up the frequencies to get the total number of observations. But if I say just want to go from frequencies to relative frequencies, what did I do here? Yeah, I just divided by the total number of observations, right? And I found that total number of observations by adding up the frequencies. Okay? All right, no questions there. Oh, I usually ask this question, but I've already shown the answer now. What should the relative frequencies always add up to? Well, if we think about this, what's in the numerators here? Just the frequencies. They all have the same denominator, which is the total number of observations. So if I add up these relative frequencies, the numerators we know are going to add up to the total number of observations, and we're dividing them all by the same thing, which is the total number of observations. If you divide anything by itself, you would get 1, right? So a good way, especially once we get to like the first Excel assignment, anytime you're calculating relative frequencies, if they don't add up to 1, you know you made a mistake, right? They should always add up to 1, okay? Any questions before we keep moving at this point? All right, so another one, the next step, I guess you could say, is relative frequencies are great. They tell you the fraction, but a lot of the time, especially I would say, like if you're presenting right, in front of a small group of people, you usually don't want to show relative frequencies. You usually want to show like percentages. Percentages are just a little easier for people to see visually and kind of think about, right? So if I have a relative frequency, right, let's think about, if I have 13 out of 25, that means the fraction of the players that had the position of pitcher here was 0.52. What would that be as a percent? Think about it this way. If I had 52 out of 100, what percent is that? 52%, right? What did you do there in your head? You just moved the decimal 2 places, right? So to get the percent frequency, we literally just take the relative frequency and multiply it by 100, right? And so this seems kind of simple. I'm sure a lot of you kind of got this and figured it out, but it does become important because we quite often in this class will go back and forth from decimals to percentages, right? Or kind of the fraction of observations in a certain category. I might ask you the percent and expect you kind of, okay, if we have it in decimal form, I can very quickly get the percentage form by multiplying by 100 or moving that decimal point 2 places. If I have the percentage form, how can I get to decimal? All I do is, I don't multiply it by 100, but I divide it by 100, right? So I can work in either direction. Right? I can, but just kind of in terms of probably the easier ways, first take the frequency, turn it into a relative frequency, take that relative frequency, which is right here, really that's just the equation we had for relative frequency, was the category's frequency divided by the total number of observations. And then to get the percentage, you just multiply by 100. Right? And then a lot of times, these are just easier for people to see and think about, right? Percentage format. Okay, so I will, be putting up that first online quiz after class today that I had mentioned. I'll be doing those on Monday. Sorry for any confusion too. I think some people thought I was going to post one after Monday. I was saying I will usually post them after class, but I wasn't going to start until kind of after the next class, not the Monday class. So this would be a kind of question you might be asked, right? I would work through something like this in class and ask you a very similar one in that online quiz on Canvas. Okay, so if I look here for 8 years, I have the top 10 causes of death, heart disease, and all these different kinds of, I guess, if we want to think about what's killing most people, I think this is essentially cancer and this is heart disease, right? And so it's killing a lot, those two things are killing a lot of people, but what percent, right? Could we see what percent of people are dying from heart disease? What percent of people in the US in this time period were dying from kind of cancer-related illness? Well, if I've got the frequencies here, right? I've got one variable, cause of death. I've got a bunch of different responses. And out of everyone in the US, this is population data, I've boiled this down into a frequency distribution. Here is the frequency of people dying from heart disease. Here's the frequency of people dying from the flu and pneumonia, right? And so how would I turn these into the percent of deaths coming from that category? What's the first step? Divided by the total. Even if I didn't show you the total here, how could you have found this? Just by, adding up all these frequencies, or adding up all the deaths. I then would take about 4 million divided by 16 million, then I would have to multiply by 100. Exactly, right? So pretty easy. I would then give you like possible answers. Now, if I'm just looking at this in my head, if this is a multiple choice, this is how my mind works. Don't get, this goes for the whole, like the length of the course, right? Don't get like married to your calculator. Like, don't trust it beyond everything, because I mean, I just know my fingers are fat enough where I hit the wrong button all the time. And if I think I did it right and I go, well, if the calculator says this, it might not always be right. And I just stop for a second and think about, well, what makes sense here? in terms of these possible answers. So I said 4 million people died out of 16 million. I'm rounding grossly there, right? Like it's like 4.4 and 16.6, but I'm just rounding very, I guess I would say irresponsibly there. But if I would think about 4 out of 16 million, that's about what? 25%. It's not going to be exactly 25 because I definitely rounded it inappropriately. But if I look at these possible responses, B and C make no sense, right? I mean, that's not even close, right? So if I just take a second and think, okay, around what's the ballpark of answers I should see here, right? I then kind of look at A and D. Well, if I had to guess, gun to my head, I guess A is probably closer. But I mean, I rounded really bad. So I don't know, maybe it is a little bit higher than that 25%. Maybe it is as high as 34. I don't know, maybe I can't think about that just looking at those numbers in my head. And so I actually go ahead and calculate it. But at least it stops me from if like I forgot a zero and I get 0.27%, I'm like, wait, no, something's gotta be wrong here, right? I forgot to do something. Oh yeah, I didn't multiply it by 100. Right? So don't ever get lost in the calculations or the computations in this class. Always try to remember, what is this statistic telling me? Well, this statistic is simply just a percent frequency. And what does that really reflect? What does that mean? Okay, just kind of roughly looking at the data, I know about what it should be. Now I just have to do some computation to get the exact number. Okay? All right, let's make sure there's no questions up here. Actually, I'll pull up that. Should send me things, but okay. And then we go, oh yeah, that's the answer, right? And so I might ask you a very similar question. Give you a data set in the online quiz, and you have to come up with percent frequency. Hopefully that's not too bad. We worked through one in class. You can always go back and look at it. And I'm not going to try to throw something new at you at those quizzes. It's something we've already kind of worked through. If you wanted to, you could do this for every single category here, right? It's just the same process. It's just a little bit more work. We'll see how we can do this in Excel on Friday and how we can do this very quickly. Okay. Oh, I didn't really mention this, but if relative frequencies have to add up to 1, the percent frequencies always have to add up to 100%, right? Same kind of thing. The relative frequency of 1, move the decimal point 2 places, you're at 100, right? Or 100% once you turn it into a percentage. Okay? I want to mention that in this slide. So once we have these frequency, relative frequency, percent frequency distributions, we want to start taking those. And like, it's great to look at this. And I can very clearly see, oh man, heart disease and cancer are killing like a lot of people, way over half if I add those two up. Right? But, if these numbers are a little bit closer and I had a couple more responses, maybe it's harder to see just looking at this data here. So I might want to turn it into some type of a picture, right? I could do a bar chart, I could do a pie chart. I mean, how many people, hopefully at this point you've all seen like a pie chart, right? Yeah, the idea is the larger slice would show you that large slice was heart disease, right? Whatever has the higher percent. So I could take this data, turn it into a pie chart or turn it into a bar chart pretty easily and get my message across visually that, whoa, why are these two bars so much higher than the rest of them? Well, because that's where most people are dying. Right? So how would I kind of create that bar chart? So we're going to try this today. I think I have this. So especially if you're watching on Zoom, there's going to be like a little hiccup here. Shows like a white screen and hopefully paper. So we're going to test this out and see what shows up better. There we go. So you probably can't, let's say, that doesn't show up real great, does it? Let's see if we do. Something like this. Does that look better? Looks pretty good. Is it really quick enough there? All right, so we'll do something like this right now. So I'm going to shorthand a bunch of stuff. But really all we're doing with a bar chart, right? On the slides, I have those percent frequencies. All I'm going to do is say, okay, here's heart disease, right? Here was malignant neoplasms, and I'm shorthanding. You probably want to write out the actual names for doing this. And then all I do is say, okay, here's my percent frequency on that y-axis. What percent of people died from heart disease? If I look at the number, it was about 32%. So we kind of draw my top of my bar there. And there's my first bar. I look at what percent was malignant neoplasms when I calculated it. Well, that was that 26%. So I kind of think about where would that be. I draw that bar. And then I kind of just keep going all the other different categories. And I can very quickly see, okay, whatever has the highest bar, that's what's killing the most people. Whatever has really low bars, maybe we don't worry about that as much. But that's really the process of creating a bar chart. It's pretty easy. I'm sure you guys have hopefully done it in the past, right? I feel like that would be like a science question on what was it? ACT has the science, right? SAT doesn't. Okay. All right, let's go back to so there will be a small delay. So some of the time, hopefully this is gonna come back to my computer. There we go. So when I use kind of this thing to do the quote unquote board work, there is going to be that kind of delay in between. So sometimes I'll probably save it so that I'm not going to be like jumping back and forth a lot. I'll be like, okay, I'll show you a picture of this in a little bit, right? And then kind of do multiple things at once with that, just so we don't lose a bunch of time kind of switching back and forth between them. And hopefully, those of you who are on Zoom, we're able to see that, okay, was that, it shows up that it's showing me, showing up to me that it's showing up to you. But I just want to double check if someone could type in the chat or speak up. Okay. Okay. So we talked about this. I'm not going to go into pie charts anymore. Got this. So if I went ahead and did that, right? Notice I put up a bar chart here. And this is really, so what I put in the y-axis here, instead of doing the percent frequency, all I did was use the frequency. So if I go back to the original data where it was like 4.4 million people died from heart disease, or maybe it was not 4.4, it was, 4.4 was the malignant neoplasm. So right, I kind of plotted that using that frequency number. Now, if I change, instead of using the frequencies to create a bar chart, and I use my relative frequencies, what's going to happen to what this looks like? There's actually going to be only one thing that changes. So if instead of using the frequencies, the millions, I use the relative frequencies, right? So I create the relative frequencies, and I then take the relative frequencies and create a bar chart. What's going to change? So yeah, it'll change my y-axis, but in terms of the bars, right? Instead, I use relative frequencies or the percent frequencies. Oops, it looks the exact same. Why? Well, if you think about it, the ratio of these categories to each other hasn't changed at all. I divided them all by the same number to turn them into relative frequencies, and then to turn them into percent frequencies, I multiplied them all by the same number. So I'm not changing the ratio. You gotta think about it this way. 1 is half of 2, right? If I multiply those both by 100, 100 is half of 200. Right? It doesn't change the ratios of those categories when we multiply and divide by the same number. So whether or not we use frequencies as our y-axis, or we use relative or percent frequencies as our y-axis, it's not going to change the visual. It just kind of depends on what information do I want my captive audience to see. If I really want to say, well, look, 30% of people are dying from heart disease. We need to care about this. If I think that sells the message better, then use percent frequencies. If I think that, look, 5.5 million people are dying, if I think that sells the message better, I use that. And there's no right or wrong answer, right? They're both going to kind of translate the same information, just kind of presenting it in a slightly different way. Okay. I could also do a pie chart. We'll see this is pretty easy to do in Excel once I have those relative frequencies or those percent frequencies. Like I said, I'm not gonna, I know you've all seen pie charts before. I feel like, the bigger the slice of the pie, the higher percent it represents, right? So, so how do I do this in Excel? Can I do qualitative and eventually can I do quantitative tables in Excel? We sure can, right? So I will show you on Friday how we create frequency tables from an original data set in Excel, right? How do we come up with those frequencies instead of just counting them by hand? how do we take those frequencies now in Excel and turn them into bar charts, pie graphs relatively easily? And we'll do all that on Friday. So, let's see that. Okay. So I'm going to stop this for a second. Actually, no, I'm just going to stop the slideshow. So I want to show you, not Zoom, I want to show you on Canvas where, so first of all, I mentioned this Monday, I did get that Learn Smart, that first Learn Smart I want you to get on. Really, that just helps you get registered for Connect and Learn Smart. And the due date on that is the end of the day Friday. So just go on, read that. We've already kind of started talking about some of the information today. We'll talk about more of it in Excel on Friday. But just get the easy points. Make sure it gets you registered so that when we start having the first Connect homework, we'll have everyone kind of ready to go. If we look at files here, I've added a new folder. I've also updated the seating chart Monday because we've had some ad drops. I'll probably update it again today because I'm sure there have been some more ad drops. Just to kind of, not move, if you were originally in the class, your day is not going to change. Don't worry about that. It's just that people have kind of come in and out. I'm going to remove some people and add the new people in. So if you added the class this week, I will try to be updating that seating chart later today, and then I'll also probably do it again on Friday. Okay. But this new folder, which is in-class data, let me see if there's any questions up here. Okay. In-class data, I've got kind of 2 Excel files up there. Friday, what we're going to do is we'll start working with this blank file. The completed one is what will, after we get through Friday's class, and maybe it'll spill over into Monday, but once we cover all the Excel material, it'll be what we built. This blank data set will eventually look like this. So we're starting with a scratch data set. So you kind of open this up here. Oh, let's download it a little crap quicker. So we've got, not the scene chart, there we go. So we've got a couple different sheets. We're going to use some of these data sets for different stuff, but the one that we'll start on is going to be on Friday. We're going to look at kind of the total number of deaths that have come from COVID. So I think this is from February to the end of July. We've got a bunch of different states. And so we'll start playing around with this data, coming up with frequency distributions, how many states had deaths within this range, build some frequency distributions out of that, nice visual bar charts, things like that. And, but yeah, when I start working on that Friday, the file to open to try to follow along with what I'm doing will be this one that has blank next to it, right? So if we go back to Canvas, we'll start working with this one. And when we're all done, we'll have something that looks, I don't know why the web browser is going so much slower. We'll have something that has graphs in it. We'll have a bunch of work done here, right? This is what we're going to be building in class Friday. But to follow along, start with that blank file, okay? All right, are there any other questions before I let you guys get out of here? Also, if you're on Zoom and you do have questions, because I know people like to come and ask me questions when class is over, I have been leaving Zoom open for a little bit afterwards. So if you want to speak up or type in the chat, I'll answer questions kind of as people are leaving on Zoom as well. So get on, get that Learn Smart done, and then be ready to start working on Excel on Friday. Okay? All right.
Like was today kind of one of the only days where we'll have to 8 notes?
So I would say, actually, here, let me, before I start